We're talking about the theory of debt and interest rates. So I want to talk about a number of technical topics first. I'm going to start with a model, an Irving Fisher model of interest, and then I'm going to talk about present values and discount bonds, compound interest, conventional bonds, the term structure of interest rates, and forward rates. These are all technical things. And then I want to get back and think about what really goes on in debt markets. So anyway, what we're talking about today is interest rates. The percent that you earn on a loan or that you pay on a loan, depending on what side of it you are. And interest rates go back thousands of years. It's an old idea. Typically, it's a few percent a year, right? The first question we want to try to think about is what explains that? Why is it a few percent a year, and why not something completely different? And why is it even a positive number? You ever think of negative interest rates? Well, these are basic questions. So I wanted to start with the history of thought. And an economist from the 19th century, Eugen von Bohm-Bawerk, who wrote a book on the theory of interest in the late 19th century. Actually, it was 1884. And he is a long, very verbose account of what causes interest rates. But basically, he came up with three explanations. Why is the interest rate something like 5%, or 3%, or 7%, or something in that range? And he said there's really three causes. One of them is technical progress, that as the economy gets more and more scientific information about how to do things, things get more productive. So maybe the 3% is, or the 5%, whatever it is the rate of technical progress. That's how fast technology is improving. But that's not the only cause that Bohm-Bawerk talked about. Another one was advantages to roundaboutness. That must be some translation from his German. But the idea is that more roundabout production is more productive. This isn't technical progress. If someone can ask you to make something directly right now, you've got to use the simplest and the most direct way to do it if you're going to do it right now. But if you have time, you can do a more roundabout way. You can make tools first and do something else that makes you a more efficient producer of this. And so maybe the interest rate is a measure of the advantages to roundaboutness. And the third cause that Bohm-Bawerk gave is time preference. That people just prefer the present over the future. They're impatient. This is behavioral economics, I suppose. This is psychology. That, you've got a box of candy sitting there, and you're looking at it and you're saying, well, I should really enjoy that next year. Well, maybe it would spoil by next year, next month, but somehow you don't. You have an impulse to consume now. So maybe the rate of interest is the rate of time preference. That maybe people why is the interest rate 5%? It's because people are 5% happier to get something now than to get it in the future. So he left that train of thought for us. This was not mathematical economics. It was literary economics. So, what your textbook author, Fabozzi, emphasizes for a theory of interest is something that came from Fisher, but it's very simple. And he says the interest rate, this is Fabozzi's distillation of Irving Fisher, the interest rate is the intersection of a supply and demand curve for savings. So I'm going to put saving, or S, on this axis. And on this axis, I'm going to put the interest rate, call that R. I don't know why we commonly use R for interest. It's not the first letter, it's in the middle of the word. And the idea is that there's a supply of saving at any time that people then wish to put in the bank or someplace else to earn interest. And the theory is that the higher the interest rate, the more people will save. So we have an upward sloping supply curve. Now this S means supply, whereas this S down here means saving, okay? And then there's a demand for investment capital, right? The bank lends out your saving to businesses, and the businesses want to know what the interest rate is. The lower the interest rate, the more they'll demand. So we have a demand curve for saving. And then the intersection of the two is the interest rate. Well, it gives the interest rate on this axis and the amount of saving on the other axis. That's a very simple story. And that's what Fabosi covers in your text. But I wanted to go back to another diagram that Fabosi et al. Did not include in their textbook, but it also comes from the 1930 book, Theory of Interest. That is a diagram that shows a two-period story. And the thing I like about this two-period diagram is that it brings out the Bohm-Valver causes of interest rate in a very succinct way. So this is the second Irving-Fisher diagram. I'm going to do a little storytelling about this. You remember the book Robinson Crusoe? It was written by Jonathan Swift in the 1700s. It was the story of a man named Robinson Crusoe who was marooned on an island all by himself and had to live on his own with no help. This is a famous story. We call it a Robinson Crusoe economy. There's only one person in the economy. So, of course, there's no trade. But we'll move to a little bit of trade. But I'm just telling you a story of the rate of... There'll be a rate of interest on Robinson Crusoe's island. Okay? So here is... I'm going to show here consumption today. And on this axis, consumption next year. All right. And I don't know what, I don't remember the novel. Did anyone here read it? You must have read, some of you must have read Robinson Crusoe. But I'm not going to be true to the story. The story I'm going to tell is that Robinson Crusoe has some food. That's all, the whole economy just is, let's say it's grain. I don't know how he got that on the island, but he's got grain. And he's deciding how much to eat this year and how much to plant for next year. So the total amount of grain he has is right here, okay? So that is his endowment of grain. And he could eat, that's the maximum he could eat. But if he eats it all, there won't be any grain to plant for next year, okay? So he'd better not eat it all, okay, or he'll starve next year. Now, in a simple linear production with technology that's linear, he can choose to set aside a certain amount of grain, which is the difference between what he has and what he's consuming. And then that will produce grain next period. So I'm going to draw a straight line. That's supposed to be a straight line. These are all supposed to be straight lines here. Okay. Okay. And that is his choice set under linear technology. I'm drawing it with no decreasing returns. The idea is that for every bushel of grain that he plants, he gets 2 bushels next year, or whatever it is, okay? And so if he were to consume nothing this period, he would have, if I drew this thing with the right slope of -2, he would have twice as much. This is the maximum he could have next period, okay? And so he could consume anywhere along this point, this line, okay? And this would be the simplest Robinson-Crusoe economy. Now, in fact, so what does he do? Remember from elementary micro theory, he has indifference curves between consumption today and consumption tomorrow. Remember these? These are like contours of his utility. We typically draw them like this, okay? So what does he do? He maximizes his utility and chooses a point that with the highest indifference curve touching the production possibility frontier. This is the PPF, the production possibility frontier. And that determines the amount that he consumes and the amount that he saves. So he consumes this amount here, and the difference between his endowment and his consumption is his saving. And then next period, he consumes this amount. All right, that's simple micro theory. That's familiar to you? So in this case, the interest rate, the slope of this line, the slope is equal to -1 plus r, where r is the interest rate. Okay, so in this case, I've told a very simple story. It has only one Bohm-Bawerk cause. It's roundaboutness. Well, maybe there's technical progress too. I don't know. It has maybe a couple of his causes. If, as time goes by, Robinson Crusoe figures out better how to grow grain, there could be a technical progress component. But preferences don't matter in this story, right? The preferences are represented by his indifference curves. And since I've got a linear production possibility frontier, impatience doesn't matter. The interest rate in this case is decided by the technology, the slope of the curve. So we don't have all of Bohm-Bawerk's causes yet. Okay. Next step. That was the simplest Irving Fisher story. The next step is, let's suppose, however, that there are diminishing returns to investment in grain. All right. That means, for example, maybe when he grows a little bit of it, he's very good at it, and he produces a big crop. But as he tries to grow more grain, he gets less productive. Maybe he has to do it on the worst land, or he's running out of water, or something is not going right. Then we would change the production possibility frontier so that it concave down. Okay? Something like that. Do you see what I'm saying? Diminishing returns to investment produce, as you keep trying to add more and more grain to your production, as you save more and more, you get less and less return. So now we have a new production possibility frontier that is more complicated. So now what happens? Suppose, forget this straight line which I drew first, and now consider a new production possibility frontier that's curved downward. Well, what does Robinson Crusoe do? Well, Robinson Crusoe picks the highest indifference curve, right, that touches this production possibility frontier. So that means he finds an indifference curve that's tangent to it. And he chooses that point. Okay? Now, okay, do you see? So this is what Robinson Crusoe would do. Now the interest rate is the slope of the tangency between the indifference curve and the production possibility frontier. It's the same for both. And this was the insight that Bohm-Bawerk maybe had a little trouble getting. There's two different things determining the interest rate. One of them is the production possibility frontier, and the other one is the indifference curves. Now we have all of Bohm-Bawerk's causes. We've got roundaboutness, we have technical progress, and we have impatience. Well, the impatience would be reflected by the slope of the indifference curves. Now I wanted to add a person to the economy. So let me start all over again. There's two Robinson Crusoes, okay, in this island. And let's start out with autonomy. They haven't discovered each other yet. They're on opposite sides of the island, okay? They have the same technology. They have the same production possibility frontier, but they live on opposite sides of the island, and they don't trade with each other. So let me start out again. This is the same diagram, and we have consumption today and consumption next year again, and we have a production possibility frontier. That's the same curve that I drew before, and the technology is the same for both of them. Okay, and let's suppose they have the same endowment. But let's suppose that Crusoe A is very patient and Crusoe B is very impatient. So Crusoe A, his utility, his indifference curves form a tangency down here. So this is A. And Crusoe B's indifference curves are up here. This is B. Okay? And so they are planning to plant. That means that Crusoe A will be saving very little. I mean, will be consuming a lot. Did I say A was the... A is the impatient one, the way I've drawn it. Consuming a lot now and not saving much for the future. But is maximizing his utility. That's why we have the highest indifference curve shown here, which is tangent. And Crusoe B has picked... Crusoe B is the very patient one. And is consuming very little this year, and it plans to consume a lot next year. So let's say they're about to plant according to these tastes, and then they find each other. Okay, now they realize there's two of us on this island. Now we're getting a real economy with two people. Okay, so what should they do? Well, the obvious thing is that there are gains to trade, and the kind of trade would be in the loan market. What they could do is, this Crusoe B is suffering a lot of diminishing returns to production. So, he really shouldn't be planting so much grain because he's not getting much return for it. Whereas this other guy on the other side of the island has very high productivity. He can produce a lot for a little bit of grain. So he should tell Crusoe, hey, you should plant some of this grain for me. So because you are more productive because you're not doing as much. Well, in short, what will happen is they'll do it through a loan. I will loan you so much grain. There's no money. A wants to consume a lot, so B will say, instead of planting so much, we'll strike a loan that will allow you to consume along your tastes. And what will happen in the economy is we'll find an interest rate for the economy that looks something. I'm going to draw a tangency. Like that's supposed to be a straight line. And on this tangent line, we have Crusoe B has maximized his utility subject to that tangent line constraint, and Crusoe A maximizes utility subject to the same constraint. And it has to be such a way that the borrowing market, as shown over here, clears. And when we have that kind of equilibrium, you can see that both A and B have achieved higher utility than they did when they didn't trade. So this is the function of a lending market. Okay, so A who wants to, did I say that right? A who wants to consume a lot this period, the production point is here. And B lends this amount of consumption to A so that A can consume a lot. He can consume this much. And B, since he's lent it to A, consumes only this much this period. But you see, they're both better off. They've both achieved a higher higher utility. And what is the interest rate in the economy? The interest rate is the slope of this line. Well, the slope of this line is minus 1 plus the interest rate. So that is the Fisher theory of interest. Let me move on to what I said I would talk about, namely different kinds of bonds and present values. The Irving Fisher story was very simple, and it had only 2 periods. So that's too simple for our purposes. So what I wanted to talk about now is is different kinds of loan instruments. And the first and the simplest is the discount bond. Okay. When you make a loan to someone, you could do it in the form of or between a company or between a government and someone, a discount bond. A discount bond pays a fixed amount at a future date, and it sells at a discount today. It pays no interest. I mean, it doesn't have annual interest or anything like that. It merely specifies this bond is worth so many dollars or euros as of a future date. And why would you buy it? Because you paid less than that amount. So let's say that it's worth $100, okay, in T periods, and T years. You know, there's some ambiguity about, I'll say T years. And I made that a capital T because, so what is a discount bond worth today? And now, we have an issue of compounding, which I want to come to in a minute, but let's assume, first of all, that we're using annual compounding, and T is in years. Okay. Then the price of the discount bond today, the price today is equal to $100 all over 1 plus R to the Tth power, where T is the number of years to maturity, T years to maturity, okay, and that's the formula, okay. In other words, 1 plus R to the Tth power is equal to 100 over P. So 100 over P is the ratio of my final value to my initial investment value if I invest in a discount bond, and I want to convert that to an annual interest rate. So this is the formula that allows me to do that. So the R is also called yield to maturity. Because the maturity is T, the time when the discount bond matures. So it's as if it's paying an interest rate, R, once per year for T years. We can infer an interest rate on it, even though the bond itself has a price, not an interest rate. I mean, we can calculate the interest rate by using this formula.